I had a little incident on my bike this morning. It's fine.
Do you have all your skin?
Hello?
Do you have all your skin still, Jerome?
Yes, that's all great.
Okay.
Okay, good. You didn't lose consciousness or anything, did you?
No, it's fine. It's fine.
Okay.
Don't worry. I'm just late. I'm sorry. Uh, so the agenda today, so we haven't met in a long time. And so we are trying to resume those meetings. And there's a lot of ongoing work at the island to plan the data collection in the winter. We're in budget season, so this is not completely finalized. And I was hoping to give an update today on this, but I think we'd need an extra week before we do that. I think we were planning to have Carter present the data packaging that he has done for SLAP 2, the newer SLAP 2 data, so that people can dive into it. And then I wanted to lead a discussion on sensory motor coupling so that we can start doing some pilot experiments with real mice. Does that sound good? Carter, do you want to introduce what you've done?
Yeah. Yeah, okay. All right, let's see. Okay, so we have one additional mouse right now for just ready for analysis. Let's see if I can see. Here on Dandy. So this was the mouse with 3 sessions that were sort of our original pilot sessions. We have this one new mouse right here. You can see the name of the file is structured a little bit differently. And also the actual structure of the file. We packaged this file with an entirely new script and new pipeline. So the structure of this file will be different, and it will be more akin to how we expect our files to look in the future. We may go back and repackage these ones, but probably not right now. In addition to this other mouse, I have one running right here. Let's see. So this is the pipeline I made on CodeOcean to package our files. I have another one running right now, so I expect this to go up in the next couple hours. And when that's up, we'll post on the forum. In the future, we plan to release basically our packaging capsules just to give people more insight on what exactly it is we're doing, but we're still working out some kinks as we continue to upload these files. So you can look forward to that. For more details about this specific mouse we have up right now, it is a VIP mouse. The experiment's all described here. The one that I'm currently uploading, so this one was from July 2nd. The one I'm currently uploading is also a mouse from July 2nd, which I checked out the genotype. I think it's a wild type mouse, but it's a different mouse.
So the other mouse is the other mouse was intended for pyramidal recording. I mean, maybe Andrew, do you want to give the context of your experiment?
Yes, so this is a C57 Black 6 wild type mouse. It was injected with two viruses. One was an AAV carrying Cree under CAMK2, so it'll express in all excitatory neurons. The virus itself was targeted to the visual cortex, upper layers of the visual cortex. And then the second virus was a Cree-dependent glue sniffer. So this will express in all pyramidal neurons sparsely in layers, approximately layers 2, 3 of visual cortex.
So we have this mouse, and then in addition to that, we have this other mouse. We have 2 sessions for that we're basically still processing and should also be up soon, definitely this week. So we have a bunch of new data coming up soon, and then we have that one file which people can get started on their analyses with. Yeah.
Andrew, do you want to say a few words about the ROI density and VIP cells so that people have right expectations?
Right. So first of all, in the VIP Cree transgenic line that we used to express glue sniffer under, as opposed to through a AAV dependent Cree, we're expressing it at all VIP neurons, so we're getting it across multiple layers and areas. The VIP neurons that we recorded in that particular experiment was a superficial VIP neuron in layer 1, as well as a deeper VIP neuron in layers 2, 3. The more superficial VIP neuron had more planar dendrites, and so those ROIs will capture just more dendrites overall, whereas the deeper ROIs in the second neuron in layer 2, 3 were pretty sparse. Just there weren't as many overall, not enough dendrites were in plane, so we just captured fewer ROIs overall. In VIP neurons, specifically with respect to pyramidal neurons in layers 2, 3, you can expect lower synaptic density, just based on the number of spines and synapses that are along dendrites per unit length. So in those experiments in DMD1, I anticipate there's probably, and Carter, correct me if I'm wrong, there's more synapses in DMD1 ROIs simply because there's more ROIs overall, and also because we expect there to be more synapses for those more planar neurons. And then the layer 2, 3 neurons, because they're more difficult to capture with less planar dendrites and lower synaptic density, you can expect fewer synapses in those recordings. Anything else?
I have a small comment that I would add, which I think that for these VIP experiments, as with your other VIP experiments, Andrew, I think it makes sense to just image like all of the synapses onto many different VIP cells. Like if the two DMDs are going to image different cells anyways, you might as well image the population of synapses onto VIP cells, which I think will be very interesting for this crowd. And you don't necessarily need to just limit yourself to the synapses onto one cell.
Absolutely, and that is what we have done with the detection of change experiments that I've been running. In this one recording session that I did with Jerome on the 2nd of July, we targeted just 2 neurons specifically and captured dendrites that were just allocated to those 2 neurons.
Questions, Alex? Maybe.
Yeah. I'm a little confused because this is a little technical. So can I ask real quick in simple terms? So do I understand correctly the following? So this is still SLAP2 and this is still glutamate imaging. And we still don't have the excitatory output of the neuron yet in terms of the 2-photon regular calcium imaging. Is that correct?
Do you want to take that, Andrew, or?
I believe for the excitatory neuron recording that we did on the 2nd of July in the C57 mouse, that we do have calcium imaging on board. I can't remember off the top of my head if that was explicitly recorded, but my intuition is that it was.
So I can comment as well. So we run the second experiment that Carter is uploading has an ROI over a soma, and in the red channel there was a calcium sensor. The caveat here is that these sensors bleach really quickly, and so we haven't figured out the secret ingredients that will allow this to work for the entire session. But essentially, we have probably 20 or 30 minutes worth of calcium in that experiment. I'm sure Casper has some thoughts there.
Only that we are very actively right now working on getting longer calcium and voltage recordings on board with these things. If you're analyzing calcium, definitely you will have to pick an early subset of trials. These calcium indicators are just... Okay, I just want to, for context, right? We image very, very fast, right, at very high SNR. The indicators that do the glutamate imaging are extremely photostable and have been highly engineered, and the red calcium indicators just are nowhere close to as good as the glutamate indicators. We are sort of working on throttling how much we illuminate the soma and greatly reducing that so that we don't sort of use up all the SNR of the red calcium indicators, but just for whatever reason, the red calcium indicators just do not perform well in our hands.
That's still exciting. I'm very excited. Will you upload that calcium signal with the SLAP?
We will. it has not yet been uploaded.
So 2 more questions. One is I do not see any link yet with either of these.
Great point. Yeah, I mean, if you have Dandy, you can just see it on Dandy, but that's a good point. We should modify the website and add the link.
Yeah, I had the link on the page.
Thank you. And then second quick question. So if I understood correctly, so you had one excitatory neuron and then you did also an inhibitory neuron, but is that correct?
2.
2 inhibitory neurons. So in the inhibitory neuron, the 2 planes are actually 2 inhibitory neurons.
That's right.
Thank you. That clarifies everything. Thank you.
And one question. Thanks, Alex, for asking all these questions. I also have a lot of those sorts of clarification questions all the time. So the 2 planes, one is layer 1, the other is 2, 3. Is it like that? Okay, thank you.
And when we try to mirror the same setup as the excitatory cells recording, so that you have the pyramidal cells and the VIP of the same proximate depth.
Thanks.
But any other question?
Yeah, last question real quick. So not only do we now have an inhibitory and excitatory neuron, and not only do we have also a calcium signal, but also this is the new paradigm, correct?
That's correct. So the
Yeah,
table,
we should get going on analysis quickly. This is very exciting.
The stimulus table is way more extensive.
I should note that neither of the inhibitory neurons have calcium sensors on board, so it is just the excitatory input to these inhibitory neurons in layer 1 and layer 2, 3. Just for clarification.
That's right. So this has the multiple blocks of oddballs and orientations that we designed together.
Right. Yeah, the stim table is more extensive, and then I mean I just packaged the main things. So we have the fluorescence and the DFF in there, the ROI locations, and then there's more metadata about like the devices and the imaging plane. Yeah, and then there's like the mean projection images and stuff like that.
Thank you for your patience as we were packaging this. It was a lot of work, and Carter put a lot of effort into doing this so that we can scale up in the future. Any other questions? Okay, so I wanted to have a little bit of brainstorming session on a potential pilot experiment we can run in the next few weeks or months around sensory motor coupling. And my rationale is that every other experiments that are passively viewing things on the screen is something we've done at the Allen for many years. We have published papers, including with some of you, along with analysis of Wu's dataset. The sensory motor coupling is a little newer to us, and I want to make sure we do this right. So that's my rationale for focusing on that. The code for implementing the coupling between the wheel and the screen is, I would say, 99% ready. So I've tested it last week on one of the MindScope on the NeuroPixel rigs, and the coupling is functioning correctly with the digital encoder of our rigs, and I've implemented this in the general oddball bonsai workflow that you can find on the website. One thing that did in the last week is to think about the coupling strength between the screen and the wheel in baseline conditions. So how much the grid, so it's, as you recollect, the goal is to have the drifting grading move backward as the mouse works forward at the same rate the mouse moves. And after some reflections with the code, I felt the most obvious ways to set this value is to move the gradings as much backward as the mouse is moving forward. So essentially measure the distance that the mouse walk on the wheel forward, and then move the grading as much back. So it has to simulate the world moving along of the natural walk. And I think, and so I figure out what I did last week is figure out using the rig geometry and the distance and all so on and so forth, and the actual spatial frequency of our gratings, because we measure this in degrees, what will be the coupling strength. I created a page on the website that is documenting this calibration. I can point you at this, but I wanted to sort of get the sense if you all agree this was the right approach to set the value initially. Are there any concern with that? Okay, so essentially that means that we are ready to push a mouse onto the rig with this protocol. And what I would like to figure out is, so, let me bring up the stimulus design so that we can discuss that with a figure. I think that will be helpful.
While you do that, really quick question for Carter. So the one session that I see on Dandai, that's the 2 inhibitory neurons.
It's VIP, yeah.
Okay. Okay, so let me share that. All right, so this is our website. You can see the page on calibration, but I think I had it here, sensory motor coupling. I'm going to clean up the pages in the next few days because I think we have grown too many. But I tried to document the calculation. I need to update this formula. I changed it yesterday to fix a mistake. But essentially, that's how I hope to document it. The code to implement the coupling is in stimulus control source sorry, wrong place. Generic oddball.bonsai. So there is here all the code to do the coupling. Then the question I have, but what I wanted to discuss today, but we have this experimental plan here. I just want to bring up the chronic session. Okay. This is here that has a cohort of mice go through sensory audible training on the cluster. And so the intent of this cluster week is have the mouse learn that they can control the gradings on the screen. And I think we probably should just pilot that as a first step, like just have mice go on the cluster, go through those 4 sessions and see how it goes. But I wanted to sort of bring this up to the group so that we can discuss any shape of this pilot that we could modify. So the intent will be to have the mice run for about I think an hour with that coupling without oddball. So it's just a simple relationship with the screen. Should we do something more complicated, or what's your opinion there?
So are you intending to train the animal to try to continuously run, or just have him spontaneously engage into multiple bouts of stop, run, stop, run?
That would be spontaneous.
Yeah.
I mean, we know that mice, a fair amount of mice spontaneously run. And so I would like to see that behavior in the context of a closed loop experiment with our screen and analyze the data. So as I said, like have a cohort of mice go through this and see what about the running, how do they behave in these conditions, upload the data in the same way as we did for SLAP2, have everyone look at it to make sure that it's good.
So in the passive condition, you had basically the gratings move, right?
In the passive condition, what do you mean?
So when the animal is not running on anything, you just present the gratings, different angles, right? The
Yeah.
stimulus. but they're actually moving, right?
They move, yes.
So now the animal is running as controlling the speed of the movement of the gratings as well.
The phase, yeah.
Right. Will there be any attempt to try to have some kind of a stationary kind of movement of the gratings at those instances where the mouse decides to briefly stop running to compare, stationary, contexts, switching from pauses to locomotion and vice versa, while you have the same gratings speed at some point?
So can you formulate this a little more precisely? So
when the animal pauses, right?
that's right.
The gratings are gonna still drift. They're not gonna stop.
I mean, in the context of the when the coupling is on, the grating just follow the mouse. So if the mouse pauses, the grating stops.
Okay, so in that moment, however many seconds the mouse decides to stop,
Yeah,
the gratings are gonna be static. They're not moving.
that's right.
So would it be beneficial to include, some variation of that where there is a little bit of movement to just compare that specific interval to the passive case in which you have a similar stimulus gratings drifting, but within the context of, locomotion episodes, right? So you know what I mean? So there are contexts that I'm coming from, I'm running, and then I pause. The gratings still move, but move at exactly the same speed they would move under the passive condition.
So, and what would you use this for? I mean,
just comparison with when I'm not running, when I'm not coupling my speed to the stimulus, the visual feedback. I just want to compare, how the properties of the neurons are going to change if the stimulus is drifting at the same speed, but from a passive context in an active context.
I see. We could do that. So for the first pilot that I'm describing today, what I'm envisioning is pure behavior. So no neuronal recording, just understanding the baseline in terms of mouse behavior. Because we have cluster rigs where there's no recording capability, and it's much less costly, much faster to deploy because we don't have to do all of those recordings. And I thought it would be helpful because it's like a quick, lower cost set of experiments that allow us to understand a little better the mouse behavior before we move it to the neural recording rigs.
Yeah, that's fine. I'm just, from a scientific standpoint, I think there is value to compare these two bouts of stopping to the passive, where you have exactly the same stimulus parameters.
So I think you're advocating for a second half of the session where we do this presentation of drifting gratings regardless of the running behavior. Is that right?
Not regardless. It's going to be it's identical to the passive condition, but only presented when the mouse decides to stop.
I see.
When the mouse re-engages back in a locomotive behavior, the coupling is as before, early in the session.
I see. And what will be the orientation of the gratings?
However they were during the moving episodes or intervals. I mean, whatever the format is to, do the change, the oddball, anything. There isn't really anything different other than when the mouse stops, you don't stop the gratings, right? They're going to continue to drift at whatever last angle they were at, or maybe a new angle if it's an oddball, whatever.
Yeah. So I wonder if what you're advocating for is two types of oddballs. One oddball anytime, whenever the mouse is running or not, and then an oddball that is only when it's static.
Yep.
Is that right?
Yes. Yes.
That could be implemented.
I just have good reasons to believe that the context within that time scale is going to make things interesting to look at.
I'm just trying to think how I would quote this. That's right. I mean, I would have to read. I mean, I can read the wheel, and if it's below a certain threshold in the second half of the session, randomly trigger an alt ball. I mean, there's a little bit of coding involved, but I think it's possible.
Right. Yeah, you just base your decision to present that stimulus or not on the threshold for the wheel movement.
Okay. Farzani?
I think I think what Karim is suggesting is interesting, but I would say maybe we get the less complicated data set first. And I think those episodes that the mouse is not moving, and as a result, the grading is also not moving, are also part of the analysis. So if we incorporate what Karim is suggesting, we will lose those. His suggestion definitely offers the comparison with the passive sessions, but I'm saying it comes at a cost. We lose part of the data set. Like we don't only analyze this data set, but that is part of the closed loop, that the mouse is not moving and that's not moving, and we want to analyze those. So that's one of my suggestions. The other, I think that was part of the confusion also that I felt it in Karim's questions. So these gradings are not drifting, they're static. Is that correct?
So let me explain it. Let me explain differently.
The closed loop. So that I don't need any clarification on that. But the gradient itself is not drifting. So the entire movement is only the parts related to the animal's movement. Is that correct? We don't have any.
I think that's so. I mean, it depends. If in the baseline conditions, that's correct. The gradings is just presented on the screen and only moves when the mouse walks.
Exactly.
And so it becomes a drifting grading through its own motion.
Yeah.
In the second half of the session, or whenever we present alt ball, that would not longer be the case, where you have now movements that are not caused by the mouse movements. Right. So I wonder if one thing that we could do, which I think will answer all points. Let me share my screen again. So you see that on the cluster, this week 1, we were for the final experiment, we were planning to have 5 sessions with sensory motor context control, like no oddball here. But in the interest of pilot, maybe it's worth swapping the last session to have oddballs, and this way we train the mouse stable, like we have a stable training for 4 days, and then in the end we present either the oddball at any time or the oddball in the way that Karim described during that session, to sort of get a sense of how the mouse react to those events. I feel like that probably would fulfill your ask.
Are you talking to me or to Farzana?
Both.
Okay. Well, yeah, I mean, I don't have a specific preference on when this condition is done. You could start it in week 2 or
that's right,
whatever. I mean, the whole purpose is to just compare when with something in common with condition 1.
That's right.
Right. We want to have some continuity of how we analyze the data. Now, when we present, when the mouse stops or the wheel's speed falls below a certain threshold, we have the gratings just static. They're frozen on the screen. So what would drive the neurons to fire? Probably nothing. I mean, nothing, of interest. But so therefore, traditionally, these episodes will be just discarded. I mean, they wouldn't really constitute anything useful. But the intent of this suggestion is to try to make these as useful as possible.
Yeah. Alex?
Yeah, so what just occurred to me is that we now have to watch for nystagmus. So I think before that could have been an issue if we have, so it's 2 monitors, I imagine, left and right, right? And so
one.
It curves around or something?
No, it's one monitor that is like covering it's a big screen, the whole right eye, and then a little bit of the front.
Oh, so it's only one side.
That's right. That's right.
Okay. So, but if you have vertical bars, which in this case, we don't do different orientations, I assume. It's just vertical,
That's right?
right?
That's right.
So in this case, it's basically temporonasal, and I think that will evoke OKN, right? So, well, we do measure eye movements, correct?
That's right. Well, on the cluster caveat, on the training cluster, we don't have the eye tracking data, because that data is, we only have had it, the hardware on the NeuroPixel rigs.
Okay, do you see what I'm getting at? So the eyes will make that movement. And so if we
Possible.
record, so yeah, exactly. So if when we want, that means the receptive field location, I don't know how much it matters given the receptive fields are so big, but since we're doing vision, a vision scientist might bring that up. So if we can get eye movements and account for that, that might help. But Karim's suggestion also is good, that if you have the exact same drift, if you could match that for the velocity, then you could say, well, visually the input is the same, but the eye movements here, that if we had horizontal gradings drifting up and down, it would be less of a concern. But since this is evoking that reflex,
I see.
the eyes
I
will
see.
move.
It's a good point. Yeah, I don't think we have the eye tracking camera. I mean, I could discuss with the team what's possible there to have like an extra session on without NeuroPixel recording on the on one rig with eye tracking to just double check there. I think it's a good feedback. So maybe
Yeah. So what I'm
Yeah.
envisioning, what happens often, let's say we find something, right? And so then what you want to do is just look at the eye movements and see that that can't explain it, or do some R-square regression and say 30% can be explained by the eye shifting. So I think that's why the data will be important. I don't think we can prevent the OKN.
Rosanne?
Sorry, Jerome, I realize I'm not too sure about the oddball. Is it the halt of the visual stimulus, or is it that we replace it with something else?
Okay, so our plan was to have 4 oddballs. One is an alt, a second one is an omission, a third one is a 45 degrees orientation, and a fourth one a 90 degrees orientation.
Okay.
So yeah, there's the typical, the one that many labs, including Georg Keller's lab, have done is an alt very often.
Right.
I think they also have omissions, but the alternative orientation is new.
Right. And then I had this more detailed question, that what is the temporal resolution here? So after how long we update the image?
The temporal resolution. Well, the wheel is recorded at on my current code. The wheel is recorded at 60 hertz. So the phase of the grading is updated at 60 hertz, the same way as the screen refresh rate.
Right.
So far, I think it's working. So it's funny. Last week I was testing my code, and I thought it was not working at some point because the grading was somehow stopping. And actually, it was the oddball that I forgot I had it in the code. But anyhow, which was good to see. I noticed it. Any other? So it looks like I can. What you're proposing is to have these training done, and then I had an extra session in the end where we do this oddballs, the oddball session essentially, to see what the mouse does, and then look into having the oddball presented regardless of the running and only when it's stationary. So I could look into doing that. And then Alex is suggesting potentially to run this session or one of the training session on a rig with high tracking so that we can check the high movements, which I think is a good feedback. Any other feedback on these? I must say I would like to move quickly on these pilots because the code is ready and we need to make sure that we can do this training. And I'm not anxious about any other of the stim, but the sensory motor coupling, I'm a little anxious to making sure that we have the right parameters. So I would like to sort of try to deploy this in the next weeks or so. Any other feedback?
This is odd feedback, but if you could also take a, this may be a little sensitive, but if you could also do a video, you might not have to show the animal, but I could imagine explaining the paradigm to people in future talks or so would be much more easy if we can just show that.
Yeah,
it might
I
also
see.
help us to get a feel for what that actually looks like. As a visual scientist, I always like to see, okay, what did you really show?
All right, so I will take a video of the screen with the wheel so that you can understand. This is, the screen is large. It's really in your face. Like it's a big screen with a big grid. I'm actually worried it's too salient, but it's a very salient stimulus. And so when, one of my concern is that I think what I see is that when the wheel turns at the typical speed of a mouse, for me, actually, the gratings move so fast that I have a hard time distinguishing what's going on. Like when the mouse is slow, it's you really can tell, but when it moves at 60 hertz full speed, it feels like a gray blur. And maybe that's what the mouse vision expect when you run fast. But this is one of the things I'm a little anxious about.
Yeah, I just looked it up. The flicker fusion frequency for mice is higher than ours, right? So an IMAX movie has 25 images a second, and we see a movie, but they can go up to 60. So there may be a concern there.
Yeah.
So I read that if we dimmed it, like
the way to maybe resolve it is, if you move the screen farther away, then you don't have to move it so fast.
Move it so fast. Well, but that's the coupling. That's essentially the coupling strength. But that's the how much I move the gratings is what I was talking at the beginning. So if I calculate, the wheel rotate a certain speed, and so when a mouse walk at normal behavior, you expect the gratings to go back. In the normal world, you expect the grating to go back a certain amount.
Yes.
And when I implement the one-to-one coupling, I feel like it's going fast because this mice, they run really fast.
Yeah, right. I guess I'm just saying like the transfer function could be such that, like, if the mouse is in the real world and there's a wall that's painted with stripes and it's really far away, of course it's going to move when it walks, but like that it can go super fast and it's still going to be moving kind of slow because of motion parallax.
I see.
So anyways, if it gets to the point where like the screen can't keep up with the mouse speed, you could still change that function and maybe move the screen further away or just change it.
So for us to move the screen is a big work because we have lots of rigs with it. It's currently at 15 centimeter from the eye. It's very close. So that's why it moves really quickly. I mean, if you want to change the transfer, like have like a non-linear transfer function where we could, but I just want like, how do we do this in a principal way?
Yeah.
So I just, again, I use AI for that. So I just looked it up, and mice don't accommodate. So I think what Jordan just said, that means, yes, if you change the coupling, it's correct. So I think in humans, you would have a discrepancy if something that should be further away and move more slowly, but your eye can tell that it's by accommodating to the light rays, that it should be further away, right? It's the number one problem with Oculus Rift and VR systems, but the mice don't. So I think if you reduce the coupling strength, that would be exactly then the same as if this object would be further away, if I don't make a mistake in my thinking now.
It's possible. Well, this is why I started with this point on coupling strength, because currently it's 1-to-1, screen at 15 centimeter, mouse walking forward, this move. And I'm just saying it's so close that gratings move really quickly. If we want to simulate a screen that is further away, we could. But I mean, it's a decision where we have to all, I think we have to discuss.
Yeah.
Sorry, I just wanted to say, I think we don't have to, because the only thing that does, the mouse can't detect the distance, right? The visual system doesn't do it. It doesn't accommodate.
No,
So
I understand.
Our lens, so I think you don't have to move the monitor. I think what Jordan said, if you change the coupling constant, it would be the same effect.
How do you choose the distance?
There's also some finicky technical details here, right? Because Jerome, you're not simulating an object at a distance. You're actually mapping it onto visual angle or like angle.
That's right.
from the mouse, right? So that's not equivalent to an object at any distance.
I mean, I'm mapping on a sphere at 15 centimeter away. Yeah.
Yeah.
But
Okay. So it's like, yeah.
It's morphed. It's morphed on the screen. Like the gratings. It's as if the mouse is walking in the tunnel.
Okay. Yeah,
I would take my primary cue for this from the previous literature rather than, especially given your concerns here, rather than like just the intuition of doing it one-to-one. I mean, I think I generally agree with Alex's point. I think there's some like niggly details about whether it's an object or not, but I would just go with the previous literature.
Yeah, that's not true. I think like though if like I guess we don't necessarily need one-to-one with the actual distance. If we want to kind of make it sub one, so that that could have a benefit because, as Jerome points out, it saturates to the point where there's not meaningful motion on the screen because the refresh rate isn't fast enough.
Well, I don't know if it's the refresh rate of the screen or the refresh rate of my visual cortex.
Oh, I see. I thought you were some hardware problems.
No.
Well, maybe you need to just take a high resolution video of the screen, just to confirm that it doesn't like glitch up at high speeds. Because if it glitches up there, this could be really annoying down the road. Because you might start to have weird prediction errors every time the mouse is running fast, and you don't know why. But then you realize, oh, the screen glitches.
I see.
Yeah, the black. If you have an iPhone, a more modern iPhone, the Blackmagic video software allows you to change the frame rate all the way up to 60. So that might work.
I think you can go up to 100 hertz now on boost camera.
Yeah.
I think so. Oh, that's a good point. I'm gonna try to do a slow-mo.
Yeah, I mean, if there's no glitching, then I don't think we need to like mess with anything else. I think that's just the thing we have to.
Artifact. Yeah, it's a good point, Jordan. Being careful about artifactual screen effect here. Yeah.
Do you use square wave gradings or do you use Gaussian filtered grading?
Sinusoidal.
Okay.
I'm going to take a camera and a high-speed camera and then send it to you guys so that you can realize what we're doing here. I think it's important. A good point. Any other?
I didn't add it, but I think that if they're, is my signal chopping?
Sorry, Jordan, I couldn't hear your first sentence.
Oh. All right, maybe it's better now. I'm on power. But my point is just that I don't want to slow us down, but I did agree with Karam's point a bit that having the inverse of the Hull prediction error could be interesting and useful. But again, as Farzana points out, we are stacking lots of things in there, so I don't think this is critical. I disagree that it's useful to have that inverse. But there might not be enough times that the mouse stops.
It's possible.
Yeah, so if the mouse doesn't stop enough, then maybe this is not going to work. But anyways, I like it. Maybe it can be piloted down the road.
I mean, you could also have the mouse stops, and then suddenly you present drifting gratings, and it actually stopped to walk because you could influence the behavior.
That's true.
I don't want to speak to the mouse, but I could see this happen.
It does. Well, every time I turn drifting gratings on in front of mice, they start walking. So
you can see an actual nice demonstration of that in a video I just posted on the chat. In this case, the mouse was not running on a treadmill or anything, but he was using 4 neurons to modulate the movement of the visual gratings. So we captured all the frame, the FOV, the mouse behavior, and the gratings all in one screen. You can see it in that video. It's a different experiment, different study, different goals, but
yeah,
just for you to see what mice do when they see visual gratings stop and move in that context. Yeah.
Okay, I'll take a look. Okay, any other feedback on this. I have a good set of action items here, so I can move on with implementing these.
Just really quick, Kareem or Jordan or you guys at the end, have you worked with this kind of things before, with closed loop or looking at this motion signal?
Yeah, so we actually did implement that on actually a floating ball. And the floating ball had camera sensors that were monitoring its rotation as the mouse locomotes. And it was rendered on the optical flow in an actual one-dimensional maze. But in this setup, the animal was rewarded for traveling a certain distance. So once they reach the end of the maze, they know they're going to get rewarded. Then the optic flow resets and then a new trial starts. I can share a video of that as well next time.
How did you choose the coupling strength?
You mean the gain of the coupling?
That's right.
We didn't change the gain in that experiment. It was a 1-to-1. So whatever the speed of the ball, it was rendered on the gratings.
I see. And
so if the animal accelerates, the gratings would move faster. If it decelerates, the animal would move slower.
How far away the screen was?
What? Oh, the screens. They were actually fairly close, about maybe I'd say no more than 10 inches.
Okay.
From the animal's fixation.
10 inches, that might be further away. Yeah.
Maybe I got that wrong. I'll check. It's not, but there were small screens because this was done under the 2-photon microscope. So
I see.
We had a space constraint. So they're like.
So you had 2 screens, 2 small screens, or?
There were 3 screens, two like this, and then 1 facing. So all of them would form like 180 enclosure. I mean, it's not curved and fancy like those.
Yeah.
Fancy screens.
In our case, it's a massive screen, so it's pretty in your face.
We didn't have that luxury of having a ton of space around under the microscope, so we had to use like iPad type of screens and then surrounded the animal with this. So
okay,
I'll share that with you guys next time. I just have to find the details.
Thank you.
But it was all implemented in. It wasn't implemented in Bonsai. It was implemented in LabVIEW.
I tried to write the Bonsai code in a way that it will be, I think, easier for other groups to modify the hardware in the Bonsai code to rerun the same thing. And so if, for instance, Kareem, you want to take our Bonsai code and run it on your rig, there's a single place to read out the digital encoder. So you would have to swap that node with whatever you have on your rig, and then it will still function. I think that should be practical. I will be looking forward to see if this actually works. But
yeah, I'd be interested to try it out. I have one-on-one students implement it. I think we're lacking still the hardware, putting the hardware together to have the Bonsai work. But I assume you have like a list somewhere that we could use to build our own here.
We could. I mean, it depends if you want to use the same disk. That's right. I mean, we have the CAD of the. I think I sent to you the link where we have all the parts list. Have you seen that?
Yeah, I think I did. It's been a while, but I'll get to it. Yeah.
Okay.
Great. Thanks.
Okay, so I want to keep a couple minutes for discussing next week. So next week we have Dr. Bosman kindly agreed to present. I'll reach out to him today or tomorrow to remind him. His publications on the sequential effect, I think, in this paper. So I think Farzaneh and Lucas pointed out this paper, and so I reach out to have him present. I think there's a lot of overlap with the analysis we've done on SLAP 2. So I'm looking forward to it. Any other things we should keep for next week? I wonder if some of you could take a look at the NBB files and provide feedback on formats to make sure that we are not missing anything, and because it's a new pipeline.
I try that.
Yeah, any other people will have some bandwidth to help there? Okay. So maybe Alex, if you could tell us if everything is squared and then you can access the data, I think that would be really helpful. Okay. Any other things we should discuss? Great. And so next week we'll have a journal club. Thanks, everyone.
See you.